Our next chapter is on the modeling distributions of data. In this section, we'll look at describing locations in a distribution. We'll find the measure in a position using percentiles, interpret the cumulative relative frequency graphs, measure a position using what's called a z-score, transform data, and define and describe density curves. Recall, standard deviation measures the average distance of the observations from the mean. It is calculated by finding the average of the squared distances and then taking the square root. Remember, the average distance squared is called the variance. One way we can describe location is to tell what percent of observations are less than it. So the pth percentile of a distribution is the value with p% of observations less than it. Example, if Jenny earned a score of 86 on her test, how did she perform relative to the rest of the class? We can see where her score is, which was greater than 21 of the 25 observations. Since 21 of 25 equals 84% of the scores, her percentile is the 84th percentile in the class's test score distribution. Likewise, we can use it for many other examples. Here's a stem and leaf plot of the wins in Major League Baseball for different teams. We can tell, for example, the Colorado Rockies, who won 92 games, where they would fall. If we look up where 92 is on the stem and leaf plot, we could then count how many there are and then how many we have total to find out what percentage it is. A cumulative relative frequency graph tells us how many percentages we have for the cumulative relative frequency. An example is first 44 presidents when they were inaugurated and what their age is. The frequency tells us how many there are. We can find the percentage very easily by taking the number divided by the total of the 44 presidents. A cumulative relative frequency tells us how many total. Starting with 2, we add the 7, now we have 9. We add on the next 13 presidents, we now have 22, and so on all the way to 44. We then find their percentages. 2 out of 44 would be 4.5%, for example. We go all the way down to the 44 out of 44, which gives us the 100%. Here's an example of how we would draw it. Take cumulative relative frequency, put the percentages along the left-hand side, labeling it. Take age at inauguration across the bottom and label that as well. We can then draw a plot of what a distribution looks like. So here was Barack Obama, who was inaugurated at age 47, unusually young. We can answer that by looking at our graph. We can also estimate and interpret the 65th percentile distribution. So watch how this would look. At age 47, we can see where that lands on the graph. Then we can estimate about what the percentage would be, roughly 11%. At 65th percentile, we can see where that distribution lies, and then check to see about what age that would fall, and in this case, 58. Percentiles and quartiles are very much related. Remember that the median corresponds to about the 50th percentile, about halfway. If we take roughly the 25th percentile, which is the median of the lower half of the ordered data, we're about quarter of the way on the data, which tells us the Q1 is about the 25th percentile. The Q3 is roughly the 75th percentile because it is at the median of the upper half of the ordered data, which is about 3/4 of the way, and we know that 3/4 is roughly 75%. A z-score in statistics is very important because it tells us how we can compare different types of distributions. It tells us how many standard deviations from the mean an observation falls and in what direction. To find it, if we take an observation from a distribution that has a known mean and standard deviation, we can find what's called the standardized value of x, which is z equals our observation, x minus the mean, divided by the standard deviation. The standardized score is often called a z-score. Jenny, who earned a score of 86 on her test, had a class mean of 80 and a standard deviation of 6.07 for the class. Her standardized score would be found by taking 86 minus 80 divided by the standard deviation, which would give us an answer of 0.99. What does the z-score then tell us? It tells us how many standard deviations from the mean an observation falls and in what direction. A z-score is not measured in the same units as the variable, so we use, for example, 0.99 standard deviations above average. Observations larger than the mean have positive z-scores, which means the observation is above average. Observations smaller than the mean have negative z-scores, which means the observation is below average. In our example, Jenny's test score is about 1 standard deviation above the mean score of the class. We can then use z-scores for doing comparisons. In our example, Jenny earned a score of 86 on her statistics test, but what if we also look at 82 on her chemistry test? The score 82 in the chemistry class had a fairly symmetric distribution of scores with a mean of 76 and her standard deviation of 4. Now what does her score of 82 tell us? Let's compare. Her z-score, as we know, for stats was 0.99. Her z-score for chemistry would be 82, her score, minus the mean of 76, divided by 4, which would give us 1.5. Another example, back to the Major League Baseball example, is what we could tell in 2009 the mean number of wins of 81 with a standard deviation of 11.4 wins. We can find and interpret the z-scores for the following teams: the New York Yankees with 103 wins and the New York Mets with 70 wins. We can then compare the two z-scores to see where each of them would fall in relation to the mean. So to do that, we would simply take the score 103 minus the mean 81 divided by the standard deviation 11.4. We could do the same with the New York Mets. Take 70, the score, number of wins, minus the mean number of wins, 81, divided by 11.4, our standard deviation. Transforming data can affect the shape, center, and spread of a distribution. Adding the same number to each observation adds that same measure of A, whatever that number is, to measures of center and location, which are the mean, median, quartiles, and percentiles. However, it does not change the shape of the distribution or measures of spread, which include the range, the IQR, and the standard deviation. So again, here's an example of a dot plot showing all of our information on some data that we got from our graphing calculator or from a computer. What would then be the effect of multiplying by a constant? If we multiplying the measures of center and location by B, we multiply the measures of spread by the absolute value of B, but it does not change the shape of the distribution. So if we multiply the same number by that value of B, again it won't change the shape. In Chapter 1, we looked at a strategy for graphical and numerical tools for describing distributions. Now we're going to look at one more step. Always plot your data, make a graph. Look for the overall pattern, that is our shape, center, and spread, and for departures such as outliers. Don't forget your socks. Calculate a numerical summary to describe the center and the spread. Sometimes the overall pattern of a large number of observations is so regular that we can describe it by a smooth curve. A density curve is a curve that is always on or above the horizontal axis and has exactly area of 1 underneath it. It describes the overall pattern of a distribution. The area under the curve and above any interval of values on the horizontal axis is the proportion of all observations that fall in that interval. So the overall pattern of this histogram of the scores of all 947 7th grade students in Gary, Indiana, on the vocabulary part of the Iowa Test of Basic Skills can be described by a smooth curve drawn through the top of the bars. The mean of a density curve is the point at which the curve would balance if made of solid material. A symmetric curve balances at its center because the two sides are identical. The mean and median of a symmetrical density curve would be equal. The median of a density curve is the balance point at which the curve would balance if it was made of solid material. The mean of a skewed curve would always be pulled away from the median in the direction of the tail. Our measures of center and spread apply to density curves as well as to actual sets of observations. A median of a density curve is the equal areas point, as I just described earlier, the point that divides the area under the curve in half. The mean is the balance point at which the curve would balance if made of solid material. And again, the mean and median are the same for a symmetric density curve. They both lie at the center of the curve. The mean of a skewed curve would always be pulled away from the median in the direction of the tail. Here's an example. In a symmetrical curve, you can see that the mean and median are exactly at the center right here of our density curve, where you have half the area on the left and half the area of the curve on the right. If we have a skewed distribution, it pulls the mean to the right in this case, which is the direction of the tail. So on this one, which is skewed to the right, remember our downhill skier standing at the top of this hill going down the slope, this will be skewed to the right. The mean is then pulled to the right with it. In the next section, we'll look at normal distributions.